Over the last half-decade, the Kepler Space Telescope has surveyed approximately 150,000 stars. Among these, roughly 600 host planets, with 1,793 confirmed and indications of 3,845 more awaiting confirmation. Among these discoveries, 9 planets have been identified with significant potential to resemble Earth, and another 9 are under consideration. Additionally, 3 more planets, though not yet confirmed, show promise as Earth-like candidates. In total, there could be as many as 660 known or inferred planets orbiting within the habitable zones of their respective stars. With ongoing observations, this number is expected to increase substantially. Astronomers estimate that around 1/5 of Sun-like stars in our galaxy possess planets in the Goldilocks zone, neither too hot nor too cold, for potential habitability. This translates to a staggering 11 billion potentially suitable planets, without even accounting for those orbiting stars different from our Sun or moons. Even after applying stringent criteria to account for various factors necessary to sustain life, such as planetary conditions and exceptions, astronomers conservatively estimate that our galaxy hosts around 100 million habitable planets. Characteristics and considerations. The quest for Earth 2.0 hinges on the exploration of exoplanets that closely resemble Earth's characteristics, offering the tantalizing potential for habitability. Key attributes of such a planet include a size and mass akin to Earth's, indicating a rocky composition and a stable surface. Essential to this quest is the presence of liquid water, necessitating the planet's location within the habitable zone of its star, where temperatures permit water to exist in its liquid state. Moreover, Earth 2.0 ideally possesses an atmosphere supportive of life, potentially containing gases like oxygen and nitrogen. Additional factors, such as the presence of a magnetic field to shield from stellar radiation and a stable orbit to mitigate extreme temperature fluctuations, are equally critical. Advanced telescopes and space missions like Kepler and TESS have identified numerous candidates exhibiting some of these Earth-like characteristics, driving forward our understanding of planetary formation and the uniqueness of our home planet. When comparing Earth 2.0 to our own Earth, it's imperative to consider both similarities and differences that could impact its habitability and potential for human colonization. Similarities include an ideal day length and seasonal cycle crucial for climate stability and supporting diverse life forms, as well as the presence of water in all 3 states, solid, liquid, and gas, essential for any form of life akin to Earth's. However, differences between Earth 2.0 and our current Earth could be significant. The type of star around which Earth 2.0 orbits, for example, could greatly influence planetary conditions, with factors such as solar radiation exposure varying based on stellar type. Gravitational disparities may also impact atmospheric conditions and life development. Additionally, the age of the planet could affect geological activity and atmospheric composition, thereby influencing its potential to sustain life. Technologies and space exploration. The pursuit of Earth 2.0 marks a significant chapter in the broader narrative of space exploration, a journey that has evolved dramatically over the past century. Initially focused on comprehending our own solar system, this quest gradually expanded to encompass the vastness of the stars beyond. The launch of the Hubble Space Telescope in 1990 represented a pivotal moment, granting astronomers unprecedented clarity in observing distant stars and galaxies. However, it was the deployment of the Kepler Space Telescope in 2009 that truly revolutionized the search for exoplanets. Kepler's mission to survey a portion of the Milky Way galaxy enabled the discovery of Earth-sized and smaller planets within or near the habitable zone of their stars. This shift from mere observation to active exploration has yielded thousands of exoplanet discoveries, a handful of which hold the promise of being potentially habitable. The quest for Earth 2.0 transcends the mere discovery of another planet. It is about unraveling humanity's place in the cosmos and pondering the existence of life beyond our solar system. Each new discovery brings us closer to answering profound questions about Earth's uniqueness and the potential for life elsewhere. Technological advancements have been instrumental in propelling this quest forward. The Kepler Space Telescope, with its unparalleled ability to detect minute changes in starlight as planets pass in front of their stars, has been instrumental in identifying potential Earth-like worlds. Subsequently, the Transiting Exoplanet Survey Satellite, TESS, launched in 2018, has taken up the mantle, surveying the sky for exoplanets around nearby dwarf stars. Ground-based observatories, such as the European Southern Observatory's Very Large Telescope, VLT, and the upcoming Extremely Large Telescope, ELT, employ sophisticated techniques like radial velocity measurements and spectroscopy to further our understanding of exoplanets. These advancements pave the way for future projects like the James Webb Space Telescope, which aim to delve deeper into the atmospheric studies of exoplanets. Advancements in the quest for Earth 2.0. The ongoing search for Earth 2.0 has unveiled a series of groundbreaking discoveries, illuminating the potential for habitable worlds beyond our own. One such revelation is the TRAPPIST-1 system, which captured global attention upon its unveiling in 2017. With 7 Earth-sized planets, including 3 nestled within the habitable zone, TRAPPIST-1 presents a compelling case for the existence of Earth-like conditions elsewhere in the cosmos. In 2015, the discovery of Kepler 452b further fueled our excitement. Often referred to as Earth's cousin, this exoplanet orbits a star reminiscent of our Sun and resides comfortably within the habitable zone. Its identification marked a significant milestone in our quest for potentially habitable worlds beyond our solar system. A year later, in 2016, Proxima Centauri b emerged as another noteworthy find. Orbiting the closest star to the Sun, this exoplanet offers tantalizing prospects for habitability. Positioned snugly within the habitable zone of its parent star. Considering the diversity of stars and even moons, the total number of habitable planets within our galaxy is conservatively estimated to be around 100 million, even after applying stringent criteria for sustaining life. Currently, astronomers are in the nascent stages of analyzing the atmospheres of these distant worlds with the hope of detecting telltale signs of life. Dr. Frank Marquis of the SETI Institute has even ventured to predict that we will discover a planet resembling our own before 2024. Australian exoplanet expert Dr. Alan Duffy from Swinburne University of Technology shares this optimism, expressing confidence that the new James Webb Space Telescope will facilitate such a discovery. The timeline for finding another Earth-like world, however, hinges on the frequency of opportunities provided by the JWST observations. Going further, SETI colleague Seth Shostak boldly predicts the discovery of extraterrestrial intelligence by 2040. Regardless of these prognostications, the search for life has become NASA's primary focus. Challenges in the dream of colonizing Earth-like planets. The vision of establishing colonies on Earth-like planets encounters numerous obstacles, with long-distance space travel emerging as one of the most formidable challenges. The vast distances involved in interstellar travel are nearly incomprehensible. Even the closest star systems are light years away, necessitating travel durations spanning years. A feat currently beyond our technological grasp. Conventional propulsion technologies, such as chemical rockets, prove insufficient for such journeys, prompting the exploration of advanced propulsion systems like nuclear thermal rockets and theoretical concepts like warp drives. In addition to technological barriers, long-duration space travel poses significant risks to human health. Prolonged exposure to microgravity leads to muscle atrophy and bone density loss, while cosmic radiation outside Earth's protective shield increases the risk of cancer and other health issues. Moreover, the psychological challenges of extended isolation and confinement exacerbate the complexity of space exploration. Even if the monumental challenge of reaching an Earth-like exoplanet is surmounted, colonizing it presents its own array of hurdles. Sustainable living technologies, including life support systems and habitat construction adapted to extraterrestrial environments, are imperative. From a biological standpoint, the effects of different gravity on human health remain uncertain, while potential environmental hazards and the psychological impact of isolation necessitate careful consideration. Addressing these challenges demands not only technological innovation, but also advances in medical science, psychology, and social engineering. Research into faster propulsion methods, health risks mitigation, and sustainable living technologies is actively underway, laying the groundwork for the feasibility of space colonization. From ion drives to bioregenerative life support systems, Ongoing efforts represent the cutting edge of current research, paving the way for humanity's future beyond Earth. Comparison between Earth and Earth 2.0. The ethical considerations surrounding the colonization of a new planet are intricate and multifaceted, presenting profound dilemmas that must be addressed. Chief among these concerns is the preservation of any potential indigenous life forms with the discovery of even microbial life, prompting significant ethical questions regarding our right to alter another world. This underscores the broader issue of planetary protection, ensuring that human activities do not harmfully contaminate other planets. Furthermore, ethical deliberations extend to decisions regarding who gets to embark on interstellar travel, with potential implications for inequality and discrimination. The exploitation of new planetary resources also sparks ethical debates, akin to those surrounding colonialism and environmental degradation on Earth. It's imperative to ensure that the mistakes of Earth's history, such as the unsustainable exploitation of natural resources, are not repeated. The ethical challenges inherent in space colonization necessitate the development of a new framework of space ethics, one that considers not only humanity's needs, but also the intrinsic value of other worlds and their potential ecosystems. Such endeavors could potentially shift humanity's perception of itself in the universe, uniting us on a global scale, but also highlighting potential divisions arising from unequal access to space colonization. As we venture into space, interplanetary responsibility and stewardship become critical considerations. There's a moral imperative to act as responsible stewards of the planets we explore and potentially inhabit, ensuring that our activities are sustainable and do not jeopardize the potential for life. International cooperation and agreement on how to approach space colonization are essential, requiring the development of legal frameworks and guidelines to ensure responsible and ethical conduct. Comparing the environmental conditions of Earth 2.0 with those of Earth is crucial in assessing the planet's habitability and planning for colonization. Understanding environmental similarities and differences, such as atmosphere, climate, water availability, and geological features, is key to ensuring the sustainability of human activities on a new planet. Lessons learned from Earth's environmental challenges, such as climate change and resource depletion, underscore the importance of sustainable practices in space colonization. Sustainable living on Earth 2.0 involves not only practical considerations, such as renewable energy sources and closed-loop systems, but also a cultural shift towards recognizing humanity's role within a larger ecosystem. This mindset is essential to ensure that human activities do not irreparably damage the new world they seek to inhabit.